It's always a pleasure to be back here. It's an honor and privilege to be able to present at this meeting, and so I thank the organizing committee for inviting me. I think like many people here in this room, Cambridge has played a big role in my career. The time I spent here has been really important to me, I think, and what I've been able to achieve, and so it's been really fun to be here and fun to be part of this meeting. Now, when I realized I was in the Frontier session, I tried to make my talk a little more general. My title is very, very specific. Modeling luminous accretion flows, but I'm going to try to broaden it into modeling accretion flows in a more general context. And maybe starting with a very, very basic introduction as to why we continue to be interested in modeling accretion disks today. It's after a subject that's been very active for many decades. Simply because, as we all know, accretion powers the most luminous sources, and therefore understanding the structure and dynamics of accretion disks in AGN and X-ray binaries is of fundamental importance in order to interpret the observations. But I think in recent decades, other reasons have emerged as well. For example, as Risa told us this morning, AGN feedback is now recognized as being very important for galaxy formation in massive halos. And more recent JWST observations are showing massive black holes very early in the universe, and perhaps super Eddington accretion plays a role in the growth of those black holes. That would be the that box that Thorsten highlighted in Martin's flow chart of growth of black holes. So rapid growth of black holes, perhaps by super Eddington accretion, may play a role. And so understanding whether in the processes of feedback and whether super Eddington accretion really can play a role in cosmological timescales is important, I think. And so these are all related to understanding accretion flows in general. And of course, Cambridge researchers have played a fundamental role in developing accretion disk theory over the decades. And I highlight a very selective set of papers from the early days. Pringle and Rees, for example, on the idea that accretion disks were powering quasars. Lindenbell and Pringle on the evolution of viscous evolution of disks. Blanford and Rees on the twin XS-jet model for feedback. And I also highlight the work of Kathy Clark on protostellar accretion disks and the role of photoevaporation. It came later than the earlier work on black hole accretion disks, but I think nonetheless recognizing the role of disks in other systems is also very, very important. So over the decades, I think Cambridge has played a huge role in developing our theory. And while this is the 50th anniversary of IOA, coincidentally, it's also the 50th anniversary of Shakur-Sanyaev, 74. I think it's fair to say this is the most highly cited paper in theoretical astrophysics, mostly for the introduction of the alpha viscosity formalism. I'm not sure it's the most read paper in astrophysics, but it is the most highly cited. And so there was just a recent conference on 50 years of accretion disks, highlighting the role and development of the accretion disk modeling. But again, this is a frontier session. So for the rest of the talk, I'll sort of focus on some of the frontiers over the last few years and where we might be going. And I have to start, of course, with the EHT image. I suspect that Sarah Markov and others have talked about this already this week, and so I don't need to say much more about it. But surely the imaging of black hole accretion by the Event Horizon Telescope has been a major step forward in the last 10 years. Now we even have polarized images, which set strong constraints on the ratio of BZ to B phi, the magnetic field direction in these accretion flows. That also places very strong constraints on the kinematics of the gas in the horizon region. And so there are remarkable constraints now on the physics of the accreting plasma that we thought we weren't going to get. EHT is meant to be a GR machine, but really it's the best instrument for measuring plasma kinetics in these relativistic regimes that we have. And so it's very, very important for constraining the models and developing, continuing our theoretical development of the models. So that's clearly been a frontier. And I think another important development in the last 50 years has been the emergence of computational methods now as a basic tool for understanding these flows. Today, numerical methods for solving the GR MHD equations are robust and reliable. There's many codes that implement these different algorithms. I highlight a few here, which are well known to the community: Harm, Hammer, Bach, and other codes, for example. And these codes enable you to model in 3 dimensions and in time-dependent manner the nonlinear regime of MHD instabilities, like the magnetorotational instability. We think that's fundamental for driving angular momentum transport and accretion in these flows. So we can gain an understanding in the nonlinear regime, something that's very difficult to do analytically, through these numerical calculations. And so doing these kind of calculations has become standard. For example, I show you the evolution of a accretion flow for a so-called MAD, a magnetically arrested disk at late times, more than 10 to the 4 m, around a rapidly spinning black hole. You've probably seen movies like this before, but you see this very low-density funnel region, a highly relativistic jets being produced along the axis. You have turbulence and accretion. This flow is in no way mad in the sense that it's not arrested. It's certainly accreting like crazy. It's a bit of a misnomer, unfortunately, that these are not really arrested. They are highly accreting. It's just that they're strongly magnetically dominated with magnetic Rayleigh-Taylor instability playing a big role. You see these bubbles of low-density plasma emerging from the inner regions. One will happen soon, I hope soon. It's going to happen, it's going to happen. There's a little one and there's another big one. So you eject these low-density, highly magnetized bubbles that then mix through KH instabilities back into the disk. So there's really complex and interesting dynamics that can be investigated through these kind of calculations. And it's become common nature to use these simulations to understand this regime. But surely another frontier has been the emergence of frontier and machines like it. These are exascale computers that have become operational in the last couple of years. The first exascale computer in the US was this machine at Oak Ridge called Frontier, quite appropriately. It's about 1.5 exaflops. That's 10 to the 18 flops. And even for astronomers, 10 to the 18 is a big number. That's a lot of flops. It's about 1 billion times faster than the first open source science computer in the US, a Cray XMP, back in 1986. And there's now a second machine installed in Argonne. It's even, in fact, a little bit faster than Frontier. It's available now for guest investigators, but it'll be open science by January. And these really are orders of magnitude larger machines, which enables orders of magnitude more computer time. The typical allocations on these machines now are 1 billion core hours to a single group. That's 100,000 computer years per year. You're able to, CPU hours per year. You're able to run on these machines. So this truly changes the kind of calculations that one can do. There is a challenge to these machines, however, and that the programming model that you need to use is more complicated. Unfortunately, these different machines each use a different programming model. They don't just run standard C++, which you might want to use on your CPUs. Instead, Intel GPUs use something called CUDA, and AMD GPUs use something called HIP, and Intel GPUs use something else called something else. And so you don't want to write a different code for each different machine, and that gets complicated to maintain different codes for all these different architectures. But fortunately, this can be solved by open source libraries. And I give you an example of Athena-K. It's a version of the Athena++ adaptive mesh MHD code. It's written using this new open source library called Cocos. It's just a C++ library that translates your source code into whatever programming model you need to run on any GPU you like. So writing your code in Cocos means you can run it on any architecture, from an iPhone to the Frontier building, using AMD GPUs. And it works exceptionally well. It gives you excellent scaling, parallel performance. So these plots show you the weak scaling of Athena-K on 2 different GPU architectures. You get nearly perfect weak scaling on these large machines. And I show you a table, not to show you the numbers, but just to say that when you have these kind of Cocos programming models, you can get performance numbers not only on standard x86 processors, but on GPUs like an NVIDIA A100, AMD, and Intel GPUs as well. And so I think Cocos is really enabling for scientific computing because it allows sluggos like me to be able to write software that runs on these machines and work on exascale machines. And so for the rest of the talk, all the results I'm showing you have all been generated on GPU clusters. All of the work we do now basically is on these machines simply because that's what's available in the US. That's where all the computer time is. And what can you do? Well, you can look at MRI turbulence at exceptionally high resolutions. This is an image from a 2-dimensional calculation run at 8,000 cubed, or 8,000 squared. It's the current density out of the plane in the MHD flow. You see emerging these very thin current sheets all over the place from the turbulence, which is winding up the magnetic field. And wherever you have these current sheets, you sometimes, not always, but sometimes get reconnection, which generates these little plasmoids. And you can, this image is not 8,000 squared on the screen, so I have to zoom in to show you a region here, which then you can see that are resolved, these little plasmoids that form in reconnection cells. So we can resolve the plasmoid-dominated regime of magnetic reconnection in resistive MHD on these machines. You might complain, well, 8,000 squared is not really exascale, that's only 2D. But of course, we're doing this now at 8,000 cubed on an exascale machine, and looking for the emergence of the exascale of these current sheets and plasmoids. So there's been a lot of interest in the plasma community that perhaps this plasmoid-dominated reconnection will change the scaling and properties of MHD turbulence. We can test this now directly for MRI turbulence and accretion disks, which I think is enabling, and that's a project underway. Exascale also involves not only single, very large calculations, but also lots and lots of smaller calculations. So for example, the EHT team has used exascale to compute literally thousands of models of black hole accretion flows at low luminosity, and then done GR ray tracing to compute millions of synthetic images, and then compare those images to the data to find the best fit models. And I like this visualization because it shows you an animation of all these models, each with different spins, orientations, magnetic field strengths, and so on in the actual underlying GR-MHD simulation, which are then all ray traced and then compared in some sort of data science way to the images from which they can then extract what are the best fit parameters for the orientation, spin, and so on of the black holes in M87 and Sagittarius A star. And I think that's also exciting and enabling stuff. Exascale also allows a lot more complicated physics. We can go beyond just GR-MHD. That's old news now. Now we can go on to even more complicated mathematical models that are more realistic, for example, for the high luminosity systems, which is really the focus of the title of my talk. Basically, if you want to go to accretion rates which give you luminosities bigger than about 10 to the minus 2 Eddington, then you really need to incorporate the radiation into the dynamics, because the radiation field plays a dominant role in energy and momentum transport in the plasma at that point. And that's really quite a, most AGN and most quasars and certainly many X-ray binaries are in this regime. And so for modeling those flows, you really want to incorporate the radiation directly. And that means solving the rate of transfer equation in GR, which while is somewhat straightforward, it's expensive to do, because you have to resolve the radiation specific intensity over many, many angles, and in principle, many frequencies as well, in order to model the radiation. So that's what we've done. We simply discretized the covariant rate of transfer equation in GR. Within each spatial grid cell, we have this little sort of geodesic mesh, which stores the specific intensity over the full 4 pi steradians, all the angles, if you like, on the sky. And then we integrate the rate of transfer equation on this geodesic mesh inside each grid cell, and so build up the full temporal, spatial, and angular distribution of the radiation field, from which we can then calculate the radiation forces and energy transport rates in the full GR problem. And so I'll show you some results from those calculations. These are now GR radiation calculations of radiation-dominated flows. Here's an accretion disk similar to what I was just showing you before, except now the Eddington ratio is close to 1. Now the radiation field is dominant. Radiation pressure is much bigger than gas pressure in this flow. And the turbulence is qualitatively different. It's much fluffier, much more filamentary. The jet region has also been modified. You don't see so many small-scale instabilities at the boundary between the funnel and the disk anymore. The radiation field is modifying that. You can see the disk is sort of settling into a denser flow in the middle here, as you can see. And so the radiation dynamics is changing the flow properties, in fact, in interesting ways. This much more compressible turbulence you get in radiation-dominated flows has been actually known for a couple of decades from shearing box simulations in the radiation-dominated regime. But now they're emerging in these full GR global models as well. And so understanding what's going on here is quite a challenge. So, for example, to show the fluffiness of these flows, if you plot the optical depth per gravitational radius, blue being very large and sort of white to red being small, the funnel region is completely optically thin, And inside the disk, there are these low optical depth bubbles where most of the matter is being squeezed into these filaments, and then there's these sort of frothy, low-density bubbles, which are nearly optically thin, bubbles of high radiation energy density and low mass density that are emerging in this flow. If I make plots of the density, mass density, on large scales, on zoom-in scales, and then the time average of the plot. So the top row is the radiation-dominated case. The bottom row is a case with no radiation for comparison. One of the most important results is that we see the emergence of this very dense, thin layer in the middle of the disk. Probably from cooling, these dense filaments are sort of collecting towards the middle of the disk. There's very thin, it's numerically resolved. At exascale, you can afford enough grid points to be able to resolve this geometrically thin flow at the middle. But it's, for example, no longer radiation pressure dominated right at the middle. In fact, gas pressure supports this very, very thin layer. And above that, it's very much radiation and magnetic pressure dominated. And in fact, this inner layer is not even accreting inwards. It's actually flowing slightly outwards. And almost all of the accretion is occurring at larger angles. And so the basic structure of these radiation-dominated disks are turning out to be somewhat different than we expected from so-called slim disk models, for example. And so understanding exactly what that structure is made possible now through these sorts of calculations. I like this image not because it's going to tell you anything new. It's a 3D rendering, but it's just a nice image. You've seen lots of artists' impressions of these disk flows. This is actual data from that calculation of the mass density with this corona and this jet emerging, relativistic jet emerging from the magnetic field. And we can do surveys now as well with different Eddington ratios. So the model I showed you was this roughly 3 Eddington model in the middle, but we've also gone up to 150 times the Eddington ratio and then down to about 10 to the minus 2, the Eddington ratio. At 10 to the minus 2, again, the bottom row is the zoom in, best to look at that bottom row. At 10 to the minus 2, we're still not resolving this very, very, very thin. We need to go to one more level of refinement, we think, to resolve this. But for these all seem resolved. And you can see a consistent pattern emerging whereby at low Eddington ratios, the photosphere, the black line, lies below the contour of 0 Bernoulli number, which is a useful demarker of where the flow is outflow and where it's a wind and where it's bound to the disk. So here you basically have an optically thin, magnetically driven wind at low Eddington ratios. And at very high Eddington ratios, it's a very optically thick radiation seems driven wind and a much thicker disk. And so we have this transition in the outflow properties with Eddington ratio from one end to another. We've also been exploring the tilt of the disk because there's no reason to believe the angular momentum of the accreting material has to be aligned with the spin of the black hole. And as soon as you do tilted disks, then much more complex dynamics can happen in the midplane or near the center because of basically general relativistic effects which try to align the spin of the angular momentum of the disk with the spin of the black hole. And so here's the time evolution of the accretion flow emerging. The MRI has grown in the disk, it's produced turbulence, generating accretion, and eventually enough magnetic flux accumulates in the horizon. You generate this relativistic jet, and you see this disk becoming aligned and the very inner regions here. So even with radiation transport, we're seeing the emergence of these aligned disks. The jet is still not 100% aligned with the spin of the black hole, but is getting there. We've, again, changed this tilt angle up to 60 degrees. We don't see any disk breaking, which is being observed in many, many previous calculations, even in the MHD regime. But with radiation transport and these radiation-dominated flows, we're not seeing disk breaking these tilted disks so far. So, in the interest of time, I'm just sort of tell you that these are providing new insights into this regime of radiation-dominated accretion. But there's other interesting questions in the field to be addressed. For example, what's the structure of these flows on larger scales? How did that gas get down there? I'm only showing you the region within a few hundred RG. How did it get there in the first place? How do you feed black holes? And exascale is enabling exploration of those questions as well. You can use very large dynamic range in spatial and temporal scales to try to resolve, kiloparsec and even tens of kiloparsec scales all the way down to the horizon. And an example I'll show is work from a student at Princeton, Minghao Guo, who's been doing these sort of zoom-in calculations of galactic halos for elliptical galaxies. You start with a hydrostatic equilibrium in a 100 kiloparsec halo. You add some turbulence and some magnetic field, and you allow a thermal cooling to generate a multi-phase medium, and you allow that to start collapsing, and you see what the structure of the flow is. And you use the zoom-in technique where you start with a large, a box which only resolves the outer scales to begin with, and as time goes by, you move the inner boundary into smaller and smaller scales to resolve smaller and smaller features, and you can go all the way down to near, within 2 orders of magnitude of the horizon, basically, from 30 kiloparsecs down to 100 RG. And what emerges is this sort of remarkable structure. On the largest scales at 30 kiloparsecs, it looks kind of like a spherical halo. But as you zoom in by a factor of 10 each step all the way down, you see the emergence of these very dense, filamentary, magnetically controlled filaments here on sort of hundreds of parsec scales. That turns into an accretion disk on tens of parsec scales. As you zoom in further, the accretion disk goes away, and you get a much more chaotic, hot accretion flow in the near horizon scale. And what's interesting is that at these intermediate scales, this is the same data, but now also plotting the Bernoulli parameter, which again marks where the regions where there's outflows. In the inner regions, you begin to see the emergence of this bipolar flow, not from Blandford-Zanayak, not from relativistic effects at the horizon, because we're not resolving the horizon, but from Blandford-Payne, from basically magnetically driven winds from the disk and larger scales. And that's going to generate feedback, and does generate feedback at the kiloparsec scales in this flow. And so by having such a large dynamic range, you can begin to address the feedback directly produced by the small scales. And the soundbite result, I think, of this work is this interesting result that despite all the complexity, despite all that complicated images, what comes out are simple power laws. The density seems to universally follow an r to the minus 1 profile, which results in the mass accretion rate following this r to the 1/2 profile. Whether or not you have hydrodynamics or MHD, whether or not you go all the way into the horizon and use jar, and he's done a few calculations that do that, you have this universal r to the 1/2 scaling for the accretion flow. Interesting because there aren't, as far as I know, any self-similar models that predict this scaling. You have r to the minus 1/2 and r to the minus 3/2 for ADAS and CDAS, but I'm not aware of this prediction. It seems to be universally emergent from these kind of turbulent accretion flows is what this scaling is. And so these may ultimately result in better AGN feedback models. There's now a project involving a collaboration with MPA to try to use more realistic halos drawn from cosmological simulations and doing new calculations that really resolve the horizon and get relativistic jet formation. And ultimately our goal over the next 5 or 10 years is to be able to have physically informed feedback models for AGN feedback. And one way we're going to get there is better algorithms. And so I'll conclude with telling you about what I think is a very interesting approach, which is being pioneered by Heron Cho, one of Ramesh Narayan's students at Harvard, using the so-called multi-zone model. I just showed you this idea of zooming in, which is very common in cosmological simulations, where over the course of time, the radial domain of which the simulation is evolving is zooming in. So you start at large scales, and then at a certain point you start resolving, you make the inner boundary smaller, and you resolve a larger range of scales, and you keep zooming in. In this case, they don't evolve the outer regions as well. They just have a finite window that moves back and forth. But you could continue to evolve these larger scales basically for free. So you could just continue to evolve all these scales from the horizon in. Of course, the problem with zoom in is that the time step gets smaller too. And so as you're evolving the flow, the calculation basically comes to a halt when you get to the inner regions, and you can't really evolve for much longer time after that. But the cyclic zoom is that you zoom back out again. You don't stop there. You zoom back out again, and you fix the inner regions with certain, you coarsen the inner solution and hold it fixed as a boundary condition. And then you do that hundreds of times. Zoom in, zoom out, zoom in, zoom out. And remarkably, this works exceptionally well for evolving even things like these tori. We've been now evolving tori with the pressure max at hundreds to thousands of RG. These tori extend out for 10 to the 4 to 10 to the 5 RG. We've been evolving them for millions of M. And the structure that results from these cyclic zooms looks identical to trying to evolve these flows with just a regular fixed mesh. You can't tell the difference. One is the truth, quote unquote, still a computational model at fixed resolution, versus the zoom. They look the same. So you get all of the structure of the flow using the cyclic zoom approach very well. And so I'll skip ahead just to say, the proof of the pudding is that if you measure the flux on the horizon, which is an important ingredient for getting the AGN feedback correct, the Blandford-Sinaiac power and the jet correct, this black line is the variation of the flux on the horizon with spin measured from a set of direct simulations by Narayan et al. These points are taken from both our own calculations to reproduce the Narayan et al. Results and these zoom calculations. And you can reproduce the feedback power as a function of spin correctly using these zoom approaches, which gives you confidence you're getting the feedback energy correct, even though you're running these calculations 10 to 100 times more efficiently. And so I think that's going to be enabling for doing these feedback modeling on cosmological timescales. So let me conclude just by saying I think both observation and theory and computation are really pushing frontiers in multiple directions. So I mentioned these low luminosity systems. I have to make the caveat that in low luminosity systems, kinetic plasma effects are probably very important. And so a very important future approach is going to be looking at the role of kinetic plasma effects, but only for these low luminosity systems. For the high luminosity systems where MHD is appropriate, we're pushing in other directions with radiation modeling. And I'll conclude with that.